Imagine the Milky Way. Every star you have ever seen in the night sky belongs to it. Hundreds of billions of suns spread across 100,000 light years of space. It takes a beam of light, the fastest thing in the universe, 100,000 years just to cross from one side to the other. Now, picture something so enormous that our entire galaxy, everything you have ever known, every star, every planet, every possibility of life within it, could fit inside it dozens of times over and still vanish in the glow. These galaxies exist. They are real. They are among the largest single structures in the known universe. And the most unsettling part is not their size, it is how they got that way. They grew by devouring other galaxies, including galaxies like ours, and they have not stopped. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. The Milky Way is enormous. You need to feel that before anything else tonight, because everything that follows depends on understanding just how vast our galaxy truly is. Only then will you grasp what it means when something makes the Milky Way look small. On a clear night, far from city lights, you can see a pale river of light stretching across the sky from one horizon to the other. That faint glow is the combined light of hundreds of billions of stars, so distant and so densely packed along your line of sight that their individual light blurs together into a milky wash. The ancient Greeks called it Galaxies, from their word for milk. We call it the Milky Way, and every single star you have ever seen with your naked eye, everyone without exception, belongs to it. Our galaxy contains somewhere between 200 billion and 400 billion stars. That range is enormous, and there's a reason for the uncertainty. Counting stars inside a galaxy you are sitting in the middle of is extraordinarily difficult. Imagine trying to count every tree in a forest while you're standing among the trunks. Dust blocks your view in certain directions. Dim trees blend into the background. You can count the ones nearby, but the farther you look, the more uncertain your tally becomes. Astronomers face the same challenge on a cosmic scale. They use brightness measurements, gravitational modeling, and statistical sampling to estimate stellar populations. But the exact total remains elusive. The best current estimates suggest roughly 200 to 300 billion stars, with considerable uncertainty in either direction. The point is not the exact number. The point is that no matter where in that range the truth falls, the answer is hundreds of billions of individual suns. Each of those stars is a sun. Some are blue giants, far larger and far more luminous than ours, burning through their fuel in a few million years. Some are tiny red dwarfs, so faint you would need a telescope to spot them, even if they were the closest stars in the sky. Red dwarfs actually make up about 70% of all stars in the galaxy, yet not a single one is visible to the naked eye from Earth. Every star you can see unaided on a clear night is brighter or more massive than the sun, or it is not a star at all, but a planet reflecting sunlight. Our star, the one that warms our world and makes life possible, is just one ordinary yellow dwarf among those hundreds of billions. It is not the biggest. It is not the brightest. It is not at the center. It sits in a relatively quiet region of a minor spiral arm called the Orion Spur, roughly 26,000 light years from the galactic core. 26,000 light years. That number deserves a moment. A light year is the distance light travels in 1 year, moving at roughly 300,000 kilometers per second. Light is the fastest thing in the universe. Nothing can outrun it. Not a spacecraft, not a radio signal, not anything with mass or energy. And yet, a beam of light leaving the center of the Milky Way right now, heading straight for Earth at that ultimate speed, would not arrive for 26,000 years. Think about what that means in human terms. When the light reaching us tonight from the galactic center first began its journey, humans were living in the depths of the last ice age. There were no cities anywhere on Earth, no agriculture, no written language, no metal tools. People were painting animals on cave walls by torchlight and shaping flint into scrapers. Every event in the entire span of recorded human civilization, every empire, every revolution, every book ever written, every song ever sung, all of it happened while the light was in transit, crossing the dark gulf between the core of our galaxy and our small planet. That is not the width of the galaxy. That is just the distance from us to its center. The Milky Way's disk of stars stretches roughly 100,000 light years from one edge to the other. Some more recent measurements push that estimate farther, suggesting the faintest outer reaches of the stellar disk may extend to 170,000 or even 180,000 light years, but even using the more conservative number, the scale is staggering. A beam of light leaving one edge of the galaxy would need 100,000 years to reach the other side. 100,000 years of traveling at 300,000 kilometers every single second, non-stop, through the void between stars, and you still have not crossed from one rim of our galaxy to the other. The galaxy is not a flat sheet of stars floating in space, it has structure. At the center is a dense, bar-shaped concentration of older stars called the galactic bulge, spanning roughly 10,000 light years across. If you could somehow visit a planet near the galactic center, your night sky would be unrecognizable. Instead of a few thousand scattered stars visible to the naked eye, you would see tens of thousands of brilliant suns packed so tightly that night would never truly be dark. The sky would glow with a permanent twilight, illuminated by the sheer density of nearby stars. Extending outward from that central bar are the spiral arms, vast curving lanes where gas and dust compress, triggering the formation of new stars. These arms are outlined by the brightest, youngest, hottest blue stars, the ones that live fast and die young, burning through their fuel in just a few million years. Beyond the visible disk is the galactic halo, a roughly spherical region populated by ancient star clusters and vast quantities of invisible dark matter. The dark matter halo alone may extend 600,000 light years or more from the center, far beyond the visible stars. Most of the Milky Way's mass is actually dark matter, not the stars and gas we can see. And the galaxy is not still. It rotates. Our sun orbits the galactic center at a speed of roughly 230 kilometers per second. That is fast enough to cross the entire continental United States in about 3 minutes. It is fast enough to circle the Earth in under 3 minutes. By any human standard, it is an absurd speed. And yet, even at that velocity, it takes the sun approximately 225 million to 250 million years to complete a single orbit around the center of the galaxy. Astronomers sometimes call this interval a galactic year. The last time the sun was at roughly this position in its orbit, Dinosaurs had just begun to evolve on Earth. The time before that, complex life on Earth was confined almost entirely to the oceans. The Sun has completed roughly 20 orbits in its entire 4.5 billion year lifetime. 20 trips around a galaxy so large that even at 230 kilometers per second, each lap takes 250 million years. Think about what all of this means for a moment. Every star you have ever seen when you looked up at the night sky, every constellation you have ever recognized, Orion, the Big Dipper, the Southern Cross, every point of light you have ever wished upon, all of it lives inside this one structure. The Milky Way contains our entire stellar neighborhood, and that neighborhood stretches for 100,000 light years in every direction from the core. From our position inside it, the galaxy is everything. It is the sum total of the visible cosmos on a clear night. If the Milky Way were the only galaxy in the universe, if it were all that existed, it would already be so vast that human beings could never explore more than a vanishing fraction of it. The nearest star to our Sun, Proxima Centauri, is a mere 4.25 light years away. And with our fastest current spacecraft, reaching it would take roughly 70,000 years. Crossing the full diameter of the galaxy at that speed would take billions of years, far longer than the galaxy itself has existed. The Milky Way is, by every human measure, incomprehensibly large. But the Milky Way is not the only galaxy, and this is where the confrontation begins. About 2.5 million light years from us, in the direction of the constellation Andromeda, there is another galaxy. You can see it on a dark night with your naked eye. It appears as a faint oval smudge, barely visible, easy to overlook. Most people who have glimpsed it probably thought it was a wisp of cloud or a trick of their vision. For centuries, astronomers didn't know what it was either. They called it a nebula, a cloud of gas within our own galaxy. It was not until the 1920s, less than a century ago, that astronomers confirmed what a few had suspected. That faint smudge was not a cloud inside the Milky Way. It was an entirely separate galaxy, millions of light years beyond the boundaries of our own. That discovery changed everything. The universe was suddenly not one galaxy, but many. And the first one we identified beyond our borders turned out to be bigger than ours. That moment deserves more attention, because the realization that the Milky Way was not everything was one of the most disorienting discoveries in the history of science. For centuries, astronomers had assumed our galaxy was the universe. Everything visible in the night sky, every star, every nebula, every cluster, was thought to exist within one vast system. The Milky Way was not merely large, it was all there was. When astronomers looked at faint smudges through their telescopes and called them nebulae, they meant clouds of gas within this single system. Spiral nebulae, as some were called, were thought to be nearby swirls of luminous gas, perhaps new solar systems forming in our galactic neighborhood. There was a famous debate in 1920 about exactly this question. Two astronomers, Heber Curtis and Harlow Shapley, argued publicly about the nature of the spiral nebulae. Shapley believed they were relatively small, relatively close objects within the Milky Way. Curtis believed they were independent galaxies, island universes as he called them, far beyond the boundaries of our own system. The debate was inconclusive at the time because neither side had definitive evidence. The answer came a few years later, when Edwin Hubble, using what was then the largest telescope in the world, the 100-inch Hooker telescope on Mount Wilson in California, resolved individual stars within the Andromeda Nebula. Among those stars, he identified a particular type called Cepheid variables, stars that pulsate in brightness with a regular period. The period of a Cepheid's pulsation is directly related to its intrinsic luminosity, how bright it actually is rather than how bright it appears. By measuring how bright Andromeda's Cepheids appeared from Earth and comparing that to how bright they actually were, Hubble could calculate the distance. The answer was staggering. Andromeda was roughly 900,000 light-years away by his initial estimate, later revised upward to about 2.5 million. It was not inside the Milky Way. It was not even close to the Milky Way. It was an entirely separate galaxy, comparable in size to our own, sitting in the void between galactic systems. The implications were immediate and overwhelming. If Andromeda was a galaxy, then the other spiral nebulae were probably galaxies too. The universe was not one system, it was millions, perhaps billions. The Milky Way, which had been everything, was suddenly one galaxy among a multitude, a single island in an ocean of space far vaster than anyone had imagined. Human significance, already diminished by the Copernican revolution that removed Earth from the center of the solar system, shrank again. We were not living in the universe. We were living in one small corner of it. That context matters for tonight's story, because it sets the emotional trajectory. We are going to repeat what Hubble experienced, but at a larger scale. We're going to start with something that feels like everything, our galaxy, and watch it become small, then smaller still. The Milky Way will shrink, not because it changes, but because the things we compare it to keep getting larger. The Andromeda Galaxy, catalogued as M31, stretches roughly 220,000 light-years across its major axis. That is more than twice the commonly cited diameter of the Milky Way. If you could somehow place the two galaxies side by side and see them from the outside, the Milky Way would look like the smaller companion, visibly less expansive, visibly less commanding. Andromeda contains hundreds of billions of stars, likely a comparable number to the Milky Way or somewhat more. Older estimates place the count as high as 1 trillion, but more recent measurements of Andromeda's total mass have revised expectations downward, suggesting the two galaxies may be closer in stellar population than astronomers once believed. What is not in dispute is that Andromeda is physically larger. Its disk stretches significantly farther, and its combined mass of stars, gas, and dark matter makes it a genuinely commanding presence, each of its hundreds of billions of suns contributing its light to the collective glow of a galaxy that makes ours look modest. If your eyes were sensitive enough to see the full extent of Andromeda in the night sky, not just its bright core, but its faint outer regions, it would span roughly 6 times the width of the full moon. That fact is extraordinary. An object 2.5 million light-years away, so distant that the light entering your eye tonight left that galaxy when the earliest members of our genus were only just appearing on Earth. And yet, it takes up a patch of sky 6 times wider than the moon. That is how large Andromeda truly is. Its apparent size on the sky is a testament to its physical scale. Most galaxies at that distance are invisible without a telescope. Andromeda is so massive and so relatively close that it registers to the naked eye as a blur of ancient light. The photons from Andromeda that reach your retina tonight began their journey 2.5 million years ago. When those photons left the outer edges of Andromeda's disk, Our ancestors were using crude stone tools and walking upright across the savannas of East Africa. Language as we know it did not exist. Art did not exist. Every invention, every idea, every civilization that has ever risen or fallen on Earth happened while that light was crossing the void between galaxies. And Andromeda is considered close. It is the nearest large spiral galaxy to our own. In cosmic terms, it is right next door, and it is getting closer. Andromeda and the Milky Way are approaching each other at roughly 110 kilometers per second. This is not a guess. It is a measurement, confirmed by precise Doppler observations of Andromeda's light, supplemented by tracking the tiny motions of stars within it using space telescopes. In approximately 4.5 billion years, the two galaxies will begin to collide and merge into a single, much larger structure. That gap is closing right now. At this very moment, as you listen to these words, the distance between the Milky Way and Andromeda is shrinking. 110 kilometers vanish every second. That is roughly 400,000 kilometers every hour. Nearly 10 million kilometers every day. In the time it takes Earth to complete one orbit around the Sun, Andromeda moves roughly 3.5 billion kilometers closer. That sounds like an enormous distance, and it is by human standards. But measured against the 2.5 million light-year gulf that separates us, it is almost imperceptible. The approach is relentless, but it is also patient. The two galaxies have been falling toward each other for billions of years, and they will continue falling toward each other for billions more before the first gravitational distortions become visible. There is no force that will stop this, no intervention, no course correction. Gravity does not negotiate. The Milky Way and Andromeda are the two most massive objects in the local group, and they have been gravitationally bound to each other since the local group formed. Every second that passes brings them closer. Every year that passes makes the eventual merger more imminent. The collision is not a possibility. It is not a probability. It is a certainty, as inevitable as the sunrise, written into the gravitational equations that govern the motion of every galaxy in the universe. The only question is what happens when they arrive. We will return to what that collision actually involves later, because the word collision means something very different when you're talking about galaxies than when you're talking about cars. For now, the important thing is this. Our galaxy, which felt infinite just minutes ago, is roughly half the diameter of a galaxy you can see with your unaided eye on a clear night. A galaxy whose disk stretches more than twice as far and whose combined mass convincingly exceeds our own. The object that seemed like everything is already being overshadowed, and we have barely left our neighborhood. The Milky Way and Andromeda are the two dominant members of a collection of galaxies called the Local Group. This is a gravitationally bound association of roughly 50 to 80 galaxies spread across about 10 million light-years of space. The third largest member is the Triangulum Galaxy, M33, located about 2.7 million light-years away. Triangulum is a spiral galaxy roughly 60,000 light-years in diameter, containing about 40 billion stars. It is smaller than the Milky Way, and far smaller than Andromeda, but 40 billion stars spread across 60,000 light-years is still a substantial galaxy by any objective standard. The rest of the local group consists mostly of dwarf galaxies, small collections of a few billion or even just a few million stars gravitationally bound to the larger members. The Large Magellanic Cloud, visible from the southern hemisphere, contains about 10 billion stars. The Small Magellanic Cloud has a few billion. There are dozens of other faint dwarfs orbiting the Milky Way and Andromeda, some so dim that astronomers are still finding new ones. These small galaxies are satellites, gravitationally trapped in the pull of their larger hosts. And as we will discover, their long-term fate is not a kind one. The local group is held together by gravity, but it is not a dense or particularly impressive collection by cosmic standards. Its galaxies are spread across roughly 10 million light-years, which sounds vast, but is relatively sparse compared to the galaxy clusters we will encounter later. Most of the local group's mass is concentrated in just two objects, the Milky Way and Andromeda. Together, they account for the overwhelming majority of the group's stellar mass, its gas, and its dark matter. Everything else, all the dozens of smaller galaxies, are essentially in orbit around one or the other of these two dominant spirals, trapped by gravity, circling slowly, and in many cases being gradually torn apart. This is worth pausing on because it introduces a dynamic that will become central to everything that follows. The smaller galaxies in the local group are not simply coexisting peacefully with the larger ones. They are being consumed. Slowly, over billions of years, the gravitational tides of the Milky Way and Andromeda are stripping stars and gas from their satellites, pulling that material into their own halos and disks. The smaller galaxies are losing mass. The larger galaxies are gaining it. This is not a future prediction. It is happening now. We can see the evidence. We can map the streams of stolen stars. And we can extrapolate forward to a time when many of these small companion galaxies will no longer exist as independent objects. They will have been absorbed, their stars scattered among the hundreds of billions already orbiting within the larger hosts. This process, the gradual consumption of smaller galaxies by larger ones, is happening in the local group on a modest scale. But the same process, amplified by denser environments and repeated over billions of years, is what builds the largest galaxies in the universe. What happens quietly in our neighborhood happens violently and relentlessly in the dense cores of galaxy clusters. And the results are structures so enormous they make the Milky Way look like a footnote. But before we move beyond the local group, take a moment to anchor the scale. The Milky Way spans 100,000 light-years. Andromeda spans 220,000. Both are spiral galaxies with sweeping arms, active regions of star formation, and immense disks of gas and dust. If these were the largest examples of their kind in the universe, the story would already be remarkable. Our galaxy, which felt limitless from our vantage point on a small planet orbiting an ordinary star, spans barely half the diameter of another galaxy sitting just 2.5 million light-years away. Now step farther out. Beyond the local group, beyond our immediate cosmic neighborhood, there are spiral galaxies that make even Andromeda look moderate. These galaxies are rare. The overwhelming majority of spirals are smaller than the Milky Way, not larger. But at the upper end, out in the tails of the statistical distribution, there are spirals of extraordinary size, and they push the boundaries of what this type of galaxy can become. One of the largest known spirals is NGC 6872, located roughly 212 million light-years away in the southern constellation Pavo. This galaxy measures approximately 522,000 light-years from the tip of one spiral arm to the tip of the other. That is more than 5 times the diameter of the Milky Way, and more than twice the span of Andromeda. To travel from one arm tip to the other at the speed of light would take more than 500,000 years. 522,000 years of photons crossing the darkness between stars. And you have only just spanned this single galaxy. Its arms have been stretched and distorted by a gravitational encounter with the smaller companion galaxy, IC 4970, which is slowly falling into it. The interaction has pulled its spiral arms outward, giving the galaxy an exaggerated wingspan that makes it one of the most visually striking spirals ever observed. Deep images show the companion sitting right against one of the extended arms, caught in the act of disturbing its host. The interaction is ongoing. The smaller galaxy is losing material to the larger one. The spiral arms are being drawn outward like threads being pulled from a sweater. NGC 6872 is not just large. It is large in part because something is already in the process of disturbing it, pulling material outward, adding to its extent. Remember that detail. It will matter enormously as this story unfolds. Even among spiral galaxies, some of the most extreme sizes are connected to gravitational interactions with companions. Size is not always intrinsic. Sometimes it is inflicted. Then there is Malin 1, discovered in 1987 and located about 1.2 billion light-years away. Malin 1 is a peculiar galaxy. Most of its disk is so faint, so diffuse, that it was completely overlooked until astronomers specifically went searching for low surface brightness objects lurking below the detection thresholds of standard surveys. For decades, this galaxy existed in plain view of every telescope, pointed in its direction, and nobody noticed it. It was hidden not by dust, not by distance, but by sheer faintness. Its stars are spread so thinly across such an enormous volume that the surface brightness of most of its disk falls below the noise floor of conventional images. Only when astronomers developed techniques to detect these ghostly, ultra-faint structures did Malin 1 reveal itself. But once you account for that tenuous disk, Malin 1 stretches roughly 650,000 light-years across. That makes it more than 6 times wider than the Milky Way. The vast majority of its stars are spread so thinly across that disk that they barely register against the blackness of intergalactic space. You could look through parts of this galaxy and see other galaxies on the far side, like looking through a fog so thin it barely dims the view. It is a structure that challenges your intuition about what a galaxy should look like, and yet is one of the largest spiral structures ever measured. Malin 1 raises an uncomfortable question. How many other enormous galaxies are out there, hiding in plain sight, too faint for our surveys to detect? The answer is almost certainly many. The census of the largest galaxies is not complete. It may never be complete because the faintest examples blend into the background and disappear. And there is UGC 2885, sometimes called Rubin's Galaxy in honor of the astronomer Vera Rubin, who studied its rotation curve in the 1980s. Rubin was one of the most important observational astronomers of the 20th century. Best known for her work demonstrating that galaxies rotate in ways that cannot be explained by visible matter alone, evidence that was instrumental in establishing the existence of dark matter. The galaxy that now carries an informal tribute to her name sits roughly 232 million light-years away and spans an estimated 460,000 light-years across. It is a massive, well-formed spiral, thick with stars, far exceeding the Milky Way in both size and stellar mass. Unlike the stretched and disturbed NGC 6872, Rubin's galaxy appears relatively undisturbed. Its spiral arms are broad and well-defined. It is simply a very large, very massive spiral galaxy, assembled over billions of years through steady accretion of gas and occasional minor mergers. Rubin's galaxy is a quietly humbling reminder that our home galaxy, which seemed so immense when we began tonight, is not even close to the upper end of what spiral galaxies can achieve. Each of these galaxies is a rung on a ladder we are climbing. The Milky Way is 100,000 light-years across. Andromeda stretches to 220,000. NGC 6872 reaches 522,000. Marlin 1 extends to 650,000. Every step up the ladder makes the previous rung feel more modest. And every step involves galaxies with hundreds of billions or trillions of stars. Galaxies so vast that light itself needs hundreds of thousands of years to travel from one edge to the other. But here is what matters most. Even the largest spiral galaxies are not the largest galaxies in the universe. They are not even close. The most enormous spirals, the ones with the most extreme wingspans and the most extended disks, top out at roughly 1 million light-years across in the most generous measurements, and the vast majority are far smaller. Spiral galaxies are beautiful, but they are constrained. A spiral is a rotating disk of gas, dust, and stars. Its structure depends on density waves rippling through that disk, maintaining the pattern of the arms. It needs ongoing supplies of cold gas to form new stars. It needs a certain gravitational balance to keep its disk stable. There is a natural ceiling to how large and how massive a rotating disk can grow before it can no longer sustain its own structure. Before the physics that makes a spiral begins to fail. The largest galaxies in the universe do not have spiral arms. They have no graceful lanes of dark dust. They have no bright blue nurseries where new stars are being born. They look nothing like the Milky Way, nothing like Andromeda, nothing like any of the vast spirals we have just described. They are something fundamentally different. They are immense, featureless, softly glowing clouds of old stars, stretching not hundreds of thousands, but millions of light-years across, sitting at the gravitational centers of enormous galaxy clusters, like ancient monarchs presiding over a court. And the way they grew to such impossible size is not by building new stars from raw gas, the way our galaxy does. It is by devouring other galaxies whole, swallowing them, digesting them, and absorbing their stars and mass into an ever-growing structure that has no natural reason to stop. These are the giant elliptical galaxies. They are the true titans, the largest single objects bound by gravity in the known universe, and they are built not through creation, but through consumption. What made them so large, what keeps making them larger, is a process called galactic cannibalism, hierarchical growth through mergers, the engine behind every rung of the ladder above this point. Understanding how it works, what it does to the galaxies involved, and why it produces structures so vastly different from our own Milky Way is the key to understanding everything that comes next. Everything we have explored so far, every galaxy we have climbed through has been a spiral. The Milky Way, Andromeda, the vast stretched out giants at the far edge of what spirals can become. They share a basic architecture, a flat rotating disk of gas and stars, sweeping arms defined by waves of compression rippling through that disk, lanes of dark dust where cold gas collapses under its own weight and ignites into new stars. Spirals are dynamic, they are alive, in the astronomical sense. They're still building stars right now, still converting raw hydrogen into luminous suns, still evolving, still growing from the inside out. When you look at a spiral galaxy, you see the ongoing work of creation. Now forget all of that. The largest galaxies in the universe look nothing like the Milky Way. They have no spiral arms, they have no dark dust lanes, they have no bright blue star-forming regions, they are not flat disks, they do not rotate in any organized way. If a spiral galaxy is like a city, alive with traffic and construction and lights being switched on and off, a giant elliptical galaxy is like something else entirely. Is like an ancient stone monument. Immense, still, and silent. There is no new construction underway. No fresh lights are being turned on. Everything that burns there has been burning for a very long time, and the fuel for making anything new ran out billions of years ago. A giant elliptical galaxy is a vast, three-dimensional swarm of old stars. Not a flat disk, but something closer to a sphere, or a flattened football, or an elongated blob, depending on the individual galaxy and the angle from which you observe it. The stars inside it do not orbit in neat, organized circles the way stars orbit in a spiral's disk. Instead, they move on random, chaotic paths, swarming in every direction like bees around a hive. Some orbit one way, some orbit the other. Some plunge nearly straight through the center and out the other side. There is no coordinated rotation, no grand pattern, just a gravitationally bound cloud of stars moving in what seems like total disorder. And the stars themselves are different. In a spiral galaxy like the Milky Way, you see a mixture. Young, hot blue stars in the arms, middle-aged yellow stars like our sun scattered through the disk, and ancient red stars concentrated in the central bulge and halo. The blue stars are the most luminous, and they give spiral arms their dramatic appearance. But in a giant elliptical, the blue stars are gone. Almost every star is old. The dominant color is not blue or white or yellow, it is red and gold. These galaxies glow with the warm, fading light of stars that were born billions of years ago and have been slowly cooling ever since. There are no bright young suns being made to replace them. The raw material for star formation, cold molecular gas, has been exhausted or expelled or heated to temperatures so extreme it can no longer collapse. Star formation has effectively ceased. Try to imagine what it would be like to exist inside one of these galaxies. Picture yourself on a planet orbiting a star somewhere in the outer halo of a giant elliptical, millions of light years from any other galaxy. Your night sky would be profoundly different from the one you know. In the Milky Way, the night sky has structure. You see the bright band of the galactic plane stretching from horizon to horizon. The concentrated glow of hundreds of billions of stars seen edge on through the disk. You see individual bright stars in the foreground, some blue, some white, some yellow, some red. You see dark patches where dust clouds block the light behind them. The sky has texture, contrast, detail. There are bright regions and dark regions. There are lanes and rifts and patches of nebulosity. The Milky Way's sky tells you that you live in a disk, that stars are concentrated in a plane, that the galaxy has geometry. Inside a giant elliptical, none of that would exist. There would be no band of light across the sky, because there is no disk. Stars are distributed in every direction, roughly uniformly, thinning gradually as you look farther from the center. Instead of a bright lane with dark patches, You would see a smooth, even glow filling the entire sky, slightly brighter in one direction, toward the center of the galaxy, and slightly dimmer in the opposite direction, toward the outskirts. There would be no dark dust lanes, because the dust was consumed or expelled long ago. There would be no bright blue stars, because none have been born in billions of years. Every star you could see would be old. Red giants, orange subgiants, fading yellow dwarfs. The sky would have a warm amber quality, suffused with the ancient light of stars that formed when the universe was young. And it would be still. In the Milky Way, the sky changes over human lifetimes, very slowly but measurably. New stars are being born in nebulae you can see with a backyard telescope. Supernovae occasionally flare up and fade. The galaxy is alive with activity. In a giant elliptical, nothing is being born. Nothing is flaring. The stars are aging quietly, cooling imperceptibly on timescales so long that nothing would visibly change across the entire span of a civilization. It would be a sky of immense beauty, but also of immense stillness. A sky that has finished its work and is now simply waiting, glowing with the embers of a construction project that ended billions of years ago. That stillness is the signature of how these galaxies were built. It is not a coincidence. It is a consequence. And understanding why requires understanding the process that assembled them. This gives giant ellipticals a particular visual quality that is hard to convey in words. They do not have sharp features. They do not have intricate structures you can trace with your eye. They are smooth, they are diffuse, they glow softly and uniformly, brightest at the center, dimming gradually toward the edges, fading into the blackness of intergalactic space with no clear boundary, no obvious place where the galaxy ends and the void begins. Their outer halos are so faint, so thinly populated with stars, that determining exactly where the galaxy stops is a genuine scientific challenge. Depending on how deep your telescope can see, depending on how much faint light you can collect before the signal vanishes into noise, you might measure a very different diameter for the same galaxy. This is an important point, and we will return to it, because it makes the question of which galaxy is the largest far more complicated than most people realize. Why do these galaxies look so profoundly different from spirals? Why are they bloated clouds of old stars instead of elegant rotating disks of young and old stars mixed together? The answer is how they were built. And the answer changes everything about how we think about the largest structures in the universe. A spiral galaxy like the Milky Way grew primarily from the inside. Gas fell inward from intergalactic space, settled into a rotating disk, and cooled. As it cooled, it fragmented under its own gravity and collapsed into stars. New gas continued to arrive, new stars continued to form, and over billions of years the galaxy built itself up, layer by layer, generation by generation, from raw material converting into luminous suns. This is internal growth. The galaxy is a factory and its product is stars. A giant elliptical galaxy grew in a completely different way. It did not build most of its stars from scratch. It did not spend billions of years patiently converting gas into suns. It grew by eating other galaxies. Smaller galaxies, medium-sized galaxies, sometimes even quite large galaxies fell into it, were torn apart by its gravity, and had their stars absorbed into its swelling mass. The giant did not make those stars. Other galaxies made them. The giant simply took them. It is the difference between a bakery that bakes its own bread and a warehouse that buys bread from 100 different bakeries and stacks it all under one roof. The product looks the same from a distance, but the process that filled the shelves is entirely different. This process is called galactic cannibalism, or more formally, hierarchical merging. It is not a metaphor. It is not artistic language. It is a literal description of how the universe assembles its largest galaxies. Gravity pulls smaller galaxies toward larger ones. When a smaller galaxy falls close enough to a larger one, tidal forces begin to strip it apart. Stars are peeled away from the outer regions first, drawn into the gravitational embrace of the larger host. The remnant core of the smaller galaxy spirals inward, losing energy through a process called dynamical friction, the gravitational drag created by the larger galaxy's own stars pulling back on it. Eventually, the smaller galaxy is completely disrupted. Its stars are scattered throughout the larger galaxy's halo. Its identity is erased. It becomes part of the giant, and the giant gets bigger. This process of spiraling inward deserves a closer look, because it is one of the most important and least intuitive mechanisms in galactic physics. When a smaller galaxy enters the halo of a larger one, it does not simply fall straight to the center. It orbits. It swings through the larger galaxy on an elongated path, passing through the halo, looping around and passing through again. Each passage takes hundreds of millions of years, but with each passage, the smaller galaxy slows down slightly. This is dynamical friction, and it works through a subtle gravitational mechanism. As the smaller galaxy moves through the larger galaxy's halo, it gravitationally attracts the stars it passes near. Those stars are pulled slightly toward it, clustering in its wake, forming a faint gravitational overdensity behind the moving galaxy like a wake behind a boat. That trailing wake of accumulated mass pulls backward on the smaller galaxy, slowing it down. The effect is small on any single passage, but it accumulates over billions of years. With each orbit, the smaller galaxy loses a little energy. Its orbit shrinks. It spirals inward, closer and closer to the center of the larger galaxy. Think of it like wading through a crowd. If you walk through a dense group of people, each person you pass has to shift slightly to let you through. Their movement creates a slight drag on you, slowing you down. The denser the crowd, the more resistance you feel. For a galaxy moving through a halo filled with stars and dark matter, the crowd is the gravitational field of all that surrounding mass. Every star the galaxy passes exerts a tiny pull. Individually, these pulls are negligible. Collectively, across hundreds of millions of years and billions of gravitational interactions, they add up to a relentless braking force that drags the smaller galaxy inexorably inward. The more massive the infalling galaxy, the stronger its gravitational pull on surrounding stars, the denser the wake it creates, and the faster it loses energy. This means that larger galaxies spiral inward faster than smaller ones. A substantial galaxy, one with tens of billions of stars, might spiral to the center in a few billion years. A tiny dwarf galaxy, with only a few million stars, might take far longer, potentially longer than the current age of the universe. This explains why galaxy clusters still contain many small galaxies orbiting in their halos. The small ones have not had time to spiral in yet. They are still out there, slowly losing energy, slowly sinking, their eventual fate sealed, but not yet realized. The large ones, however, have already been consumed. They fell inward first, arrived at the center first, and were absorbed into the growing central giant. This is why the brightest cluster galaxy is so much more massive than anything else in the cluster. It has been preferentially fed the largest victims, the ones that spiral in fastest. The biggest meals arrive first. And the giant at the center has been collecting them for billions of years. This is not speculation. We can see it happening right now, all across the observable universe. Galaxies in the process of being devoured, galaxies that have recently been devoured, and galaxies showing the unmistakable scars of ancient meals. The evidence is overwhelming, and we will walk through it in detail soon. But first, you need to understand why this process builds something that looks so different from a spiral. When two spiral galaxies merge, the ordered rotation of their disks is destroyed. Think about what happens. Each galaxy has its own disk, its own rotation, its own orbital structure. The two disks are oriented at different angles, rotating in different directions, approaching from different trajectories. When they begin to interact gravitationally, the tidal forces scramble everything. Stars that were peacefully orbiting in neat circles are yanked sideways, flung onto new paths, sent plunging through the center, or hurled outward into extended orbits. The beautiful spiral pattern, which depends on organized, coherent rotation, is torn apart. By the time the merger is complete, the two populations of stars from the two original galaxies are swirling together in a chaotic, randomized swarm. The flat disk is gone. What remains is a roughly spherical or ellipsoidal cloud of stars orbiting in every direction. An elliptical galaxy. The gas suffers a different fate. Unlike stars, which are tiny points separated by vast empty space and almost never physically collide during a merger, gas clouds are extended. They fill space. When two galaxies merge, their gas clouds crash into each other directly. The collisions shock the gas, heating it to millions of degrees. Some of that heated gas is blown out of the galaxy entirely by the energy released. Some falls inward and may trigger a brief, violent burst of star formation, using up the remaining cold fuel in a cosmic bonfire. The central supermassive black hole, present in nearly every large galaxy, may also become active during a merger, swallowing infalling gas and releasing torrents of energy that heat the remaining gas further, preventing it from cooling and forming stars. The result is that after the merger, the new elliptical galaxy has very little cold gas left. The raw material for making stars has been consumed, expelled, or heated beyond use. Star formation shuts down. The galaxy becomes red and dead, populated only by the aging stars it already has, with no way to make new ones. This is the fundamental insight. The biggest galaxies in the universe did not grow by being the best star factories. They grew by being the most effective predators. They consumed other galaxies and inherited their stars. The stars in a giant elliptical were not born there. They were born in dozens or even hundreds of smaller galaxies over the course of billions of years, each with its own history, its own chemical enrichment, its own generations of stellar life and death. Then those galaxies were swallowed, and their stars became part of the giant. The giant is not a birthplace, it is a graveyard. A magnificent, glowing graveyard of consumed galaxies. And here is where environment becomes everything. Galaxies are not distributed randomly through space, they cluster. Gravity draws them together into groups and clusters. Concentrations of dozens to thousands of galaxies bound together in a shared gravitational well. The local group, which contains the Milky Way and Andromeda, and about 50 to 80 smaller galaxies, is a modest example. It is a loose, relatively quiet collection, but there are far denser structures out there. Galaxy clusters can contain hundreds or even thousands of large galaxies, packed into a region just a few million light years across. Surrounded by halos of dark matter so massive, that the cluster bends the light from more distant galaxies behind it, warping space-time itself into a gravitational lens. At the center of nearly every large galaxy cluster sits one dominant galaxy. It is always the largest. It is always the most massive. It is almost always an elliptical. And it is almost always surrounded by a vast, faint halo of stars extending far beyond its visible core. An envelope of stellar debris from all the galaxies it has consumed over cosmic time. Astronomers call these objects brightest cluster galaxies, often abbreviated as the letters BCG. Some of the most extreme examples are also classified as CD galaxies, a designation that refers to their supergiant envelopes of diffuse light. These are the apex predators of the cosmic food chain. They sit at the bottom of the deepest gravitational wells in the universe, and everything around them slowly falls inward. Why does the biggest galaxy always end up at the center? Because the center of a cluster is where gravity is strongest, where the density of galaxies and dark matter is highest, and where the opportunities for mergers are most frequent. Galaxies orbiting within a cluster lose energy over time through gravitational interactions. As they lose energy, they sink toward the center, where the dominant galaxy is waiting. When they arrive, they are consumed. Their stars are added to the giant's halo. Their gas is heated and absorbed. Their dark matter merges with the cluster core. The biggest galaxy gets bigger because it sits at the point where all the food converges. This is hierarchical growth in its purest form. The universe builds structure from the bottom up. Small galaxies form first, from the primordial gas that existed after the Big Bang. Those small galaxies merge to form medium-sized galaxies. Medium-sized galaxies merge to form large galaxies. And large galaxies, if they happen to live at the center of a dense cluster, continue to merge with everything that falls into their gravitational reach, growing and growing and growing across billions of years. The biggest galaxies are the ones that have eaten the most. And the ones that have eaten the most are the ones that live in the densest environments, where the supply of galaxies to consume is greatest. Consider the Virgo cluster. It is the nearest large galaxy cluster to us, centered roughly 54 million light-years away. The Virgo cluster contains somewhere between 1,200 and 2,000 galaxies. At its heart sits M87, one of the most studied galaxies in the history of astronomy. M87 is a giant elliptical galaxy. It contains roughly 1 trillion stars. Its visible body stretches across at least 120,000 light-years, comparable to the Milky Way's disk. But it is not a disk. It is a vast, three-dimensional cloud of ancient stars, and its faint outer halo extends much farther, perhaps 300,000 light-years or more, depending on where you draw the boundary between the galaxy and the intracluster light. The diffuse glow of stars that have been stripped from other galaxies and now float freely within the cluster's gravitational field. M87 did not get this large by forming stars efficiently. It got this large by sitting at the gravitational center of the Virgo cluster for billions of years and absorbing every galaxy that wandered too close. Look more closely at M87 because it rewards examination. This is not just a large galaxy. It is a galaxy surrounded by an extraordinary system of globular clusters, dense, spherical collections of hundreds of thousands of stars each. The Milky Way has about 150 known globular clusters orbiting in its halo. M87 has roughly 15,000. 15,000 globular clusters, each one a tightly bound swarm of ancient stars, orbiting within the galaxy's enormous gravitational domain. Where did they all come from? Most of them were not born inside M87. They were brought in by consumed galaxies. When a smaller galaxy is devoured, its globular clusters are stripped away and absorbed into the host galaxy's halo, along with everything else. Each consumed galaxy contributes its own complement of clusters. Over billions of years across dozens or hundreds of mergers, the collection grows and grows. The number of globular clusters orbiting M87 is itself a record of how many galaxies it has consumed. 15,000 clusters accumulated over a cosmic lifetime of feeding. It is another form of fossil evidence, another layer of the archaeological record preserved in the body of the giant. M87 also produces an enormous jet of material, a beam of high-energy particles launched from the vicinity of its central black hole, extending outward for roughly 5,000 light-years. This jet is powered by the supermassive black hole at the galaxy's center, the same black hole whose shadow was directly imaged for the first time in 2019 by the Event Horizon Telescope collaboration. That image, a glowing ring of superheated gas surrounding a dark central void, was the first direct visual confirmation of a supermassive black hole's event horizon. The black hole itself contains roughly 6.5 billion times the mass of our Sun. It is one of the most massive black holes ever measured, and its size is a direct consequence of the galaxy's merger history. Each consumed galaxy brought its own central black hole. Those black holes sank to the center through dynamical friction and eventually merged with M87's own black hole, adding their mass to its total. The black hole grew with the galaxy, meal by meal, merger by merger. Every layer of M87 tells the same story. Its globular clusters, its stellar halo, its jet, and its black hole are all records of the same process, written in different forms. It is a galaxy whose entire structure is a monument to consumption, and everything about it, its mass, its size, its extraordinary population of ancient star clusters, exists because it has spent billions of years at the gravitational center of a galaxy cluster, absorbing everything that wandered too close. But M87 is not the largest. The Virgo cluster is a moderately sized cluster. There are denser, more massive clusters elsewhere in the universe, and at the centers of those clusters sit even larger galaxies. The Coma cluster, roughly 330 million light-years away, is one of the richest galaxy clusters in the nearby universe. It contains more than 1,000 large galaxies and thousands of smaller ones, all bound together by gravity and a vast halo of dark matter. At its center sits NGC 4889, a galaxy containing an estimated 2 trillion stars or more. That has roughly 10 times the stellar population of the Milky Way. NGC 4889 is enormous by any standard, a colossal elliptical galaxy that dwarfs most others in its vicinity, built through the same process, consuming galaxy after galaxy across cosmic time. Its central black hole is among the most massive ever detected, estimated at roughly 21 billion solar masses, evidence of a long and violent merger history. 21 billion solar masses. That number deserves a moment to land. Our Sun is an ordinary star, but it contains more than 99% of all the mass in the solar system. Everything else, every planet, every moon, every asteroid, every comet, all of it combined amounts to less than 1% of the Sun's mass. And this single black hole at the center of NGC 4889 contains 21 billion times that mass. compressed into a region of space smaller than our solar system. The event horizon, the boundary beyond which nothing can escape, is roughly the diameter of the orbits of the outer planets. An entire solar system's worth of space swallowed into a gravitational point of no return. That black hole did not form in a single event. No star, no matter how massive, could produce a black hole this large through its own collapse. It was assembled over billions of years through the same hierarchical process that built the galaxy around it. Each merger brought another galaxy, and each galaxy brought another black hole. Those black holes sank to the center, spiraled together, and merged. Each merger added mass. Each merger made the host galaxy more massive, deepening its gravitational well and increasing the dynamical friction that would drag the next victim inward. The black hole and the galaxy grew together, fed by the same process, each one a record of the same billions of years long history of consumption. The Coma Cluster as a whole is one of the best studied galaxy clusters in astronomy. It was one of the first clusters where Fritz Zwicky, in the 1930s, noticed that the galaxies were moving too fast to be held together by the visible matter alone. Their velocities implied far more mass than the stars and gas could account for. Zwicky proposed that some form of invisible mass, which he called dark matter, must be providing the extra gravity. He was right, though it took decades for the rest of the scientific community to accept it. Today, we know that galaxy clusters are dominated by dark matter. In the Coma Cluster, dark matter outweighs ordinary matter by roughly 5 or 6 to 1. The visible galaxies, the stars, and the hot gas glowing in X-rays are just a small fraction of the total mass. Most of the cluster is invisible, a vast halo of dark matter providing the gravitational scaffolding that holds everything together and that draws everything inexorably toward the center, where the giant is waiting. And then there are the clusters that host the galaxies at the very top of the observed scale. Galaxies like IC 1101, a supergiant elliptical at the center of the Able 2029 cluster, roughly 1.04 billion light-years from Earth. IC 1101 is often cited as one of the largest galaxies ever discovered, with estimates for its diameter ranging from roughly 2 million to 6 million light-years, depending on how deeply you can trace its faint outer halo. That enormous range tells you something important. The size of a galaxy like this is not a single, settled number. It depends on where you stop counting stars, how much faint light your telescope can detect, and what you define as belonging to the galaxy versus belonging to the surrounding intracluster medium. The diffuse stellar envelope blends so gradually into the background that there is no sharp edge. Drawing a boundary is an act of measurement convention, not physics. Different studies using different instruments and different depth thresholds can reach genuinely different answers for the same galaxy. What is not in dispute is the sheer scale. Even at the lower end of estimates, IC 1101 stretches far beyond anything a spiral galaxy could achieve. It contains trillions of stars. Its halo of faint ancient light extends outward for enormous distances, a vast cloud of stellar wreckage accumulated across billions of years of mergers. Every star in that halo was once part of another galaxy, a galaxy that no longer exists as a separate entity. Each one was consumed, digested, and assimilated. The giant carries within itself the remains of hundreds or possibly thousands of smaller galaxies, each with its own history, each now just a contribution to the diffuse glow. And this is the pattern everywhere we look. At the center of the Perseus cluster, roughly 240 million light-years away, sits another dominant galaxy. In the Centaurus cluster, another. In the Fornax cluster, another. Every massive cluster has one, and it is always the largest, always an elliptical, always the product of a long history of consumption. The galaxy that sits at the gravitational center feeds first and feeds most, growing inexorably while its neighbors are whittled away. This is the engine behind every rung of the size ladder above the spiral galaxies. The reason each step up the ladder exists is not because nature built a bigger factory. It is because gravity in dense environments funnels smaller galaxies into larger ones. The biggest galaxies live at the hearts of the biggest clusters, because that is where the feeding is best. They did not earn their size through internal productivity. They earned it through position, through sitting at the bottom of the deepest gravitational wells, where everything that falls inward eventually ends up inside them. And this raises a question that might already be forming in your mind. If these giants grew by eating other galaxies, what does that process actually look like? When two galaxies collide, what really happens? What does it do to the stars? What does it do to the gas? What does it do to the shapes we see? The answer is stranger and more violent and more beautiful than you might expect. Because when galaxies merge, almost nothing you would predict actually occurs. And the evidence of every single merger is written into the structure of the resulting galaxy like a fossil record waiting to be read. When you hear the word collision, your brain builds a picture instantly. Two objects slamming together, metal crumpling, glass shattering, force meeting force, surface against surface, a violent moment of impact where two things that were separate are suddenly, catastrophically, no longer separate. Everything in your daily experience tells you that a collision is destructive, sudden, and physical. Two cars hitting each other. Two rocks crashing together. Two billiard balls clacking on a table. Contact. Impact. Damage. Now forget that picture completely. Because when galaxies collide, almost none of that happens. A galaxy merger is one of the most counterintuitive events in the universe. Two galaxies, each containing hundreds of billions of stars, slam into each other at speeds that can exceed hundreds of kilometers per second. And the stars almost never touch. Not rarely, not infrequently, almost never. In the entire history of a typical galaxy merger, involving hundreds of billions of stars on each side, the number of direct stellar collisions is likely zero. Not a handful, not a small percentage, essentially zero. The reason is space. Not outer space in the general sense, but the space between stars. Stars are unimaginably far apart relative to their own sizes. Our sun has a diameter of roughly 864,000 miles. That is large by everyday standards, but the nearest star to the sun, Proxima Centauri, is over 4 light-years away. If you shrank the sun to the size of a ping-pong ball, roughly 1.5 inches across, the nearest other ping-pong ball representing Proxima Centauri would be about 700 miles away. That is roughly the distance from New York City to Indianapolis. Two tiny balls separated by 700 miles of empty space. Now multiply that by hundreds of billions. That is what a galaxy looks like on the inside, is overwhelmingly, astonishingly, almost perfectly empty. The stars are tiny bright specks scattered through a void so vast that the chance of any two of them physically colliding during a merger is negligibly small. So if the stars do not collide, What happens? The answer is gravity. And gravity does not need contact to do extraordinary things. When two galaxies approach each other, their gravitational fields begin to interact long before their stellar populations overlap. Gravity reaches across space. It does not need to touch. It pulls. And when two systems, each containing hundreds of billions of solar masses of material, begin pulling on each other, the tidal forces become immense. Tidal force is the difference in gravitational pull across an extended object. The near side of one galaxy is pulled harder toward the other than the far side. This difference stretches the galaxy. It distorts it. Stars on the outer edges, the ones least tightly bound, are the first to feel it. They are tugged sideways, pulled out of their orbits, drawn into long arcs and streamers extending outward from the galaxy like taffy being stretched. These are tidal tails, and they are among the most visually dramatic features in all of astronomy. Some of the most famous images ever taken by the Hubble Space Telescope show galaxies in the act of merging, their tidal tails sweeping outward for hundreds of thousands of light years, vast ribbons of displaced stars and gas drawn out by the gravitational interaction between two colliding systems. The antennae galaxies, a pair of merging spirals catalogued as NGC 4038 and NGC 4039, roughly 45 million light-years away, display two enormous tidal tails extending outward like the antennae of an insect, which is how they got their name. Those tails are made of stars that were ripped from the outer disks of the two galaxies by the gravitational forces of the encounter. Every star in those tails was once orbiting peacefully in a spiral arm. Now it has been flung into intergalactic space, still bound to the system, but no longer part of any organized structure. The mice galaxies, NGC 4676, show a similar picture. Two interacting galaxies trailing long tails of displaced material. These galaxies are roughly 300 million light-years away, and their tails stretch for hundreds of thousands of light-years. The stars in those tails are not being destroyed. They are being relocated. Gravity is reshuffling them, pulling them out of the orbits they occupied for billions of years and placing them on entirely new trajectories. But while the stars pass through each other like two swarms of bees flying through each other in an open field, the gas does something very different. Galaxies contain gas, enormous quantities of it, cold molecular hydrogen, warm atomic hydrogen, hot ionized plasma. This gas fills the space between stars, concentrated especially in the disks of spiral galaxies, where it serves as the raw material for star formation. Gas is not like stars. Stars are tiny, dense points separated by enormous voids. Gas is diffuse. It fills volume. It occupies space in a way that stars do not. And when two galaxies merge, their gas clouds do collide. Directly. Violently. When gas from one galaxy slams into gas from the other at hundreds of kilometers per second, the result is devastating. The gas shocks. It compresses. Temperatures spike to millions of degrees. In some regions, the compression triggers exactly the opposite of what you might expect. Instead of destroying the capacity for star formation, the shock waves compress pockets of gas to such extreme densities that they collapse under their own gravity and ignite into new stars. The merger triggers a starburst, a furious, short-lived episode of star formation that can produce new stars at rates tens or even hundreds of times higher than what a normal galaxy achieves in its steady state. The antennae galaxies are a prime example. Their overlapping region, the zone where the two galaxies' gas disks are crashing into each other, is one of the most intense star-forming environments in the nearby universe. Thousands of new star clusters are being born there right now, forged in the violence of the collision. But the starburst is self-defeating. It consumes the cold gas at an extraordinary rate. The same process that ignites all those new stars also burns through the fuel supply. Gas that would have lasted billions of years in a quiet spiral galaxy is used up in tens or hundreds of millions of years during a starburst. When the gas is gone, star formation stops, and it does not restart because there is no cold gas left to fuel it. Meanwhile, the energy released by the starburst and by the central black holes, which often become active during mergers as gas is funneled inward, heats whatever gas remains. Hot gas cannot collapse. It cannot cool efficiently enough to fragment into stars. It sits there, glowing in X-rays, filling the merged galaxy and the surrounding cluster environment with a diffuse, superheated medium that resists further star formation. This is why giant elliptical galaxies are red and dead. The mergers that built them also destroyed their ability to make new stars. The very process of growth carried within it the mechanism of sterilization. The role of the central black hole in this sterilization deserves a closer look because it is one of the most dramatic examples of feedback in astrophysics, a process where the consequence of growth actively prevents further growth of a particular kind. During a major galaxy merger, as gas is funneled inward by gravitational torques and tidal forces, some of it reaches the vicinity of the central supermassive black hole. As gas spirals towards the black hole, it forms an accretion disk, a swirling, superheated platter of material compressed to extreme temperatures by friction and gravitational energy. The temperatures in this disk can reach millions of degrees. At these temperatures, the disk radiates furiously, pouring out energy across the electromagnetic spectrum, from radio waves through infrared and visible light to ultraviolet and X-rays. The luminosity can be extraordinary. An actively accreting supermassive black hole can outshine the entire galaxy around it, producing more light from a region smaller than our solar system than hundreds of billions of stars produce combined. This is an active galactic nucleus, and during the peak of a major merger, it can become one of the most luminous objects in the universe. But the energy does not simply radiate away harmlessly. Some of it couples to the surrounding gas. Powerful jets of material are launched from the poles of the accretion disk, beams of particles moving at close to the speed of light, drilling outward through the galaxy and into the surrounding cluster medium. Radiation pressure and winds from the accretion disk push outward in all directions, heating and expelling gas from the galaxy's central regions. The energy injected into the surrounding gas is immense. It heats the gas to temperatures where it can no longer cool efficiently, preventing it from condensing into the dense clouds that would otherwise collapse into new stars. This is the mechanism that kills star formation in the merged galaxy. The very act of feeding the black hole generates so much energy that it heats or expels the remaining cold gas, removing the raw material for future star formation. The black hole, in a sense, regulates its own food supply. By consuming gas aggressively during the merger, it releases enough energy to prevent any more gas from cooling and becoming available. It is a self-limiting process, but the limit it imposes is permanent. Once the cold gas is gone, it does not come back. The galaxy is left with a massive, quiet black hole at its center, surrounded by trillions of aging stars, with no mechanism to produce new ones. Red and dead. Not because the galaxy ran out of gas on its own, but because its own central engine blew the remaining fuel supply apart. Now, let us talk about what gravity does to the structure of the galaxies involved. Imagine two spiral galaxies approaching each other. Each has a beautifully organized disk. Stars orbit the center in nearly circular paths, all in roughly the same plane, all in roughly the same direction. The spiral arms trace out a coherent pattern maintained by density waves. Everything is orderly. Everything rotates together. When the two galaxies begin to interact, that order is systematically destroyed. The tidal forces pull stars out of their circular orbits. The gravitational potential of the merging system is no longer symmetrical. It is lumpy, time-varying, chaotic. Stars that were on stable circular orbits are now moving through a gravitational landscape that changes with every passing million years as the two galaxies swing around each other, pass through each other, swing back, pass through again. Each passage scrambles the orbits further. Stars are deflected onto new paths. The flat disk warps, buckles, and eventually dissolves entirely. By the time the two galaxies have fully merged, which can take 1 to 3 billion years from first contact to final coalescence, the organized rotation of both original disks has been erased. What remains is a cloud of stars moving on random, chaotic orbits in 3 dimensions. An elliptical galaxy. This is not a theory stitched together from assumptions. It is one of the most thoroughly tested predictions in modern astrophysics. Computer simulations of galaxy mergers, run on supercomputers that track the gravitational interactions of millions of simulated star particles, reproduce the process in stunning detail. You can watch a simulated merger unfold. Two elegant spirals approach each other. Tidal tails are drawn out. The galaxies swing past, distort, loop back, pass through each other again. Gas shocks and star formation flares. The disks warp and dissolve. After a few billion simulated years, a single, smooth, roughly ellipsoidal cloud of stars remains where two spirals once existed. The simulations match observed mergers at every stage, from the first tidal distortions to the final relaxed elliptical. The physics is understood, the process is confirmed, and every single time, the larger galaxy wins. When two galaxies of unequal mass merge, the outcome is not symmetrical. The smaller galaxy is disrupted first and more completely. Its stars are stripped away and absorbed into the larger galaxy. Its structure is destroyed. Its identity is erased. The larger galaxy is disturbed, certainly. It may develop tidal features. Its disk may warp. It may undergo a starburst. But it retains the bulk of its structure. And when the merger is complete, the remnant is recognizably descended from the larger progenitor, now swollen with the added mass and stars of its consumed companion. This is why the biggest galaxies keep getting bigger. Each merger adds mass. Each merger adds stars. Each merger pushes the giant further up the size ladder. And because the giant sits at the center of a cluster where gravity funnels new victims inward, the process repeats. A galaxy falls in. It is consumed. The giant grows. Another galaxy falls in. It too is consumed. The giant grows again. Over billions of years, the central galaxy has consumed dozens, possibly hundreds of smaller systems. Each one adds a layer of stars to the giant's halo, like geological strata being laid down one on top of another. And this is where the story becomes truly remarkable, because those layers are still there. They have not been erased. They have not blended into uniformity. If you look carefully, If you look deeply enough, you can see them. The fossil record of every galaxy ever consumed is written into the structure of the giant that ate it. The most dramatic evidence comes in the form of stellar shells. These are concentric arc-like features, faint ripples of light encircling the outer regions of many giant elliptical galaxies. They look like the rings that form when you drop a stone into still water, frozen in place. Each shell is made of stars from a consumed galaxy. When a smaller galaxy falls into a larger one, its stars do not immediately blend into the host. They oscillate. They plunge inward through the giant, pass through the center, and coast outward on the other side. Then they slow, stop, and fall back inward again, like a pendulum swinging back and forth through the center of a gravitational well. At the turnaround points, the outermost extent of each oscillation, stars pile up briefly. They linger there, moving slowly before falling back. This creates a visible overdensity, a faint arc of light at a specific radius from the center. Each shell corresponds to a different oscillation, a different turnaround point, a different moment in the digestion of a consumed galaxy. Deep imaging of giant ellipticals has revealed these shells around a remarkable fraction of them, but no nearby example is more vivid or more instructive than Centaurus A, catalogued as NGC 5128. At roughly 12 million light-years away, it is one of the closest giant elliptical galaxies to Earth, and it is one of the most studied objects in extragalactic astronomy. What makes Centaurus A extraordinary is not just its size, it is what it looks like. In most images, Centaurus A appears as a smooth, glowing elliptical body, round and featureless in the way ellipticals tend to be. But slicing directly across its center, cutting the galaxy almost in half visually, is an enormous lane of dark dust. It is strikingly out of place. Elliptical galaxies are not supposed to have prominent dust lanes. Dust belongs to spiral galaxies. It sits in their disks, concentrated along the plane of rotation, mixed in with the cold gas that fuels star formation. An elliptical galaxy, by definition, has consumed or expelled as gas and dust. The presence of a thick, dark dust lane cutting across an otherwise smooth elliptical body is a glaring contradiction, and it tells you exactly what happened. Centaurus A consumed a spiral galaxy, recently by cosmic standards, perhaps a few 100 million years ago. The spiral was disrupted. Its stars were absorbed into the elliptical's halo, but the dust from the spiral's disk has not yet been fully dispersed. It is still there, sitting in a band across the center of the galaxy, the undigested remnant of a meal that has not yet been fully broken down. And there is more. Surrounding the main body of Centaurus A, extending outward into the faint reaches of its halo, deep imaging reveals a system of concentric shells, those same faint arcs of piled up stars we described moments ago. The shells are the oscillating remnants of the consumed spiral's stellar population, stars that plunge through the giant and are now swinging back and forth through its gravitational well, piling up at their turnaround points. The dust lane tells you what was eaten. The shells tell you when and how the digestion is proceeding. Centaurus A also hosts powerful radio lobes extending outward for hundreds of thousands of light years on either side. Jets launched by its active central black hole, which was likely stirred into activity by the very same merger that deposited the dust lane. In a single object, you can see every stage of galactic cannibalism playing out at once. The victim's remains, the gravitational digestion, and the energetic aftermath of a black hole awakened by the influx of fresh material. Centaurus A is not an anomaly. It is simply close enough and recent enough in its merger history that the evidence has not yet faded. Given enough time, the dust lane will dissipate, the shells will blur and spread, the radio lobes will fade, the galaxy will settle into the quiet, featureless glow of a typical giant elliptical, its crime erased by time. But right now, at this moment in cosmic history, it is caught in the act. It has not yet finished digesting its last meal, and because it is only 12 million light years away, we can study it in remarkable detail. Reading the evidence of consumption written across its face, beyond shells, there are tidal streams. These are long, thin rivers of stars arcing through the halos of large galaxies. Each one the stretched out remains of a smaller galaxy that was torn apart by tidal forces. The stars in a tidal stream share a common origin. They move together on similar orbits, tracing out the path of the galaxy that was destroyed. Astronomers can measure the positions and velocities of these stars and reconstruct the orbit of the consumed galaxy, essentially rewinding the clock and watching the merger in reverse. Our own Milky Way has tidal streams. The Sagittarius dwarf galaxy, a small satellite galaxy discovered in 1994, is being ripped apart by the Milky Way right now. Its stars are being pulled into a long stream that wraps almost completely around our galaxy. It has already made several passes through the Milky Way's disk, losing stars with each passage, leaving a trail of stellar debris that astronomers have mapped in detail. The Sagittarius dwarf is not being consumed in the distant future. It is being consumed now, in our time, as we watch. Our own galaxy is a cannibal, actively feeding on a smaller companion. And it is not the only meal in progress. The large and small Magellanic Clouds, the two most prominent satellite galaxies of the Milky Way, visible from the southern hemisphere as fuzzy patches of light, are also being slowly consumed. A vast stream of hydrogen gas called the Magellanic Stream trails behind them, stripped away by the Milky Way's gravitational tides. That gas stretches across more than 100 degrees of the sky, a river of material being pulled from the Magellanic Clouds into our galaxy. In several billion years, the Magellanic Clouds themselves will be fully absorbed. Their stars will join the Milky Way's halo. Their gas will feed new star formation in our disk. They will cease to exist as independent galaxies and become part of ours. Sit with that for a moment. The Milky Way, our galaxy, the structure that contains every star you have ever seen in the sky, is actively destroying other galaxies right now. Not in some distant future, not in theory. Right now, tonight, as you listen to this, the Sagittarius dwarf galaxy is being torn apart by our galaxy's tidal forces. Its stars are being peeled away and scattered into a stream that wraps around the Milky Way like a slowly dissolving ribbon. Hundreds of millions of stars that once belonged to an independent galaxy, a galaxy with its own structure, its own history, its own billions of years of existence, are being absorbed into ours. That galaxy is dying, it is being consumed, and we are the ones consuming it. The Magellanic Clouds are next, though their consumption will take considerably longer. From the southern hemisphere, you can look up and see them with your naked eye. Two fuzzy patches of light hanging in the darkness, looking peaceful and permanent. But they are not permanent. The Magellanic Stream, that vast ribbon of hydrogen gas trailing behind them, is the evidence of their slow disintegration. Every year, more material is stripped away. Every orbit around the Milky Way brings them a little closer to dissolution. In a few billion years, the Magellanic Clouds will be gone. Their stars will be part of our halo. Their gas will have been folded into our disk. They will exist only as a chemical signature in the Milky Way's stellar populations, a faint trace of distinct composition amid the homogenized mass. The way a dissolved sugar cube exists only as sweetness in a cup of tea. This is what galactic cannibalism looks like from the inside. We do not see it as violence. We see it as a quiet sky on a clear night. But the violence is there, written in the streams of displaced stars, the rivers of stripped gas, the slowly diminishing masses of our satellite galaxies. Our galaxy is gentle with us. It is not gentle with them. The same process is happening around Andromeda. M32, one of Andromeda's small companion galaxies, shows evidence of having already been partially stripped. It is compact and dense, as though its outer layers were peeled away by Andromeda's tidal forces. M110, another Andromeda satellite, shows tidal distortions, suggesting it is being stretched and will eventually be consumed. The giant spiral is feeding on its companions just as our galaxy feeds on ours. But the most powerful evidence of past mergers comes from the stars themselves. Different galaxies produce stars with different chemical compositions. A galaxy that formed stars early, from gas that had not yet been enriched by many generations of supernovae, produces stars with low concentrations of heavy elements. A galaxy that formed stars later, from gas recycled through multiple stellar generations, produces stars richer in iron, carbon, oxygen, and other elements forged in stellar cores and scattered by supernova explosions. When you consume a galaxy, you inherit its stars, and those stars carry the chemical fingerprint of their birthplace. Astronomers can measure the chemical compositions of individual stars in the halos of nearby giant ellipticals. They can also measure the ages. When they do, they find something striking. The stars are not uniform. They come in distinct populations. Some are very old and metal poor, relics of ancient dwarf galaxies consumed early in the giant's history. Others are younger and more chemically enriched, the remains of larger, more evolved galaxies consumed later. The different populations are sometimes spatially separated, occupying different regions of the halo, different shells, different streams. Each population is a fossil, a remnant of a galaxy that once existed independently, with its own star formation history and its own chemical evolution. Reading the stellar populations of a giant elliptical is like reading geological layers in a cliff face. The deepest, oldest layers correspond to the earliest mergers. The more recent layers sit closer to the surface. Each layer has its own composition, its own age, its own story. A geologist can look at a cliff and reconstruct millions of years of Earth's history, reading the record of ancient seas, volcanic eruptions, and ice ages preserved in stone. An astronomer can look at a giant elliptical galaxy and reconstruct billions of years of cosmic history, reading the record of consumed galaxies preserved in starlight. This forensic approach has been applied with spectacular success using modern telescopes. Deep surveys with the Hubble Space Telescope and ground-based observatories have revealed tidal features, shells, and streams around a large fraction of elliptical galaxies. Some studies suggest that more than 50% of nearby elliptical galaxies show detectable signs of recent or ongoing interactions when imaged deeply enough. The evidence is not subtle, and it is not ambiguous. These galaxies wear their histories on their surfaces, written in the faint arcs and filaments and chemically distinct populations scattered through their halos. And the record goes deeper still. The kinematics, the motions of stars within a giant elliptical, also carry information about past mergers. Different populations of stars move differently. Stars inherited from one consumed galaxy might orbit predominantly in one direction. Stars from another consumed galaxy might orbit in a completely different direction. By carefully measuring the velocities of thousands of individual stars, astronomers can identify these kinematic substructures. Groups of stars that move together because they share a common origin. Each substructure is the ghost of a former galaxy, its stars still moving in loose concert even after billions of years, like the fading echo of a voice in a vast hall. Taken together, the shells, the streams, the chemical populations, and the kinematic substructures paint a comprehensive picture. Giant elliptical galaxies are not monolithic objects that formed in a single event. They are composites, assembled over billions of years from the wreckage of many smaller galaxies. Every giant carries within itself the archaeological record of its entire feeding history, layer upon layer of consumed companions, each one identifiable by its chemical signature, its stellar age, its orbital fingerprint, and sometimes its visible shell or stream. This is galactic cannibalism laid bare. Not as a theoretical model, not as a computer simulation, but as observable fact, written in starlight across the bodies of the largest galaxies in the universe. The giants didn't create their magnificence, they consumed it. And the evidence is everywhere, if you know how to look. What remains now is to follow this process to its ultimate conclusion, to climb the final rungs of the ladder and see the very largest galaxies ever observed. The monsters at the centers of the most massive clusters, still feeding, still growing, still consuming everything that falls within their reach. Because the most extraordinary thing about galactic cannibalism is not that it happened. It is that it never stopped. We have climbed the ladder rung by rung. We began with the Milky Way, 100,000 light years across, and felt its enormity. We stepped up to Andromeda, more than twice our galaxy's span. We crossed into the rare oversized spirals, galaxies stretching 500,000 light years from arm tip to arm tip. Then we left spirals behind entirely and entered the realm of the giant ellipticals, those immense, featureless clouds of ancient stars built not through creation, but through consumption. We learned how they grew. We learned what mergers do to the galaxies involved. We read the fossil record written in their shells and streams and chemically distinct stellar populations. Now, it is time to climb the final rungs. The galaxies we are about to encounter are the largest single gravitationally bound structures in the known universe, and the environments that built them are among the most extreme places the cosmos has to offer. To understand these galaxies, you first have to understand the places where they live, because no galaxy becomes this large in isolation. Environment is everything. The biggest galaxies sit at the centers of the most massive galaxy clusters, and those clusters are not randomly scattered through the universe. They occupy the nodes of the cosmic web. If you could zoom out far enough to see the distribution of matter across billions of light years, you would not see galaxies sprinkled uniformly through space like sugar on a table. You would see a network. Vast filaments of dark matter and gas stretch across hundreds of millions of light years, connect in dense knots where the filaments intersect. Those knots are the galaxy clusters. Between the filaments are enormous voids, regions hundreds of millions of light years across, that are nearly empty. The universe has structure, and that structure looks eerily like a web, with threads and junctions and hollow spaces in between. Galaxy clusters form at the intersections of filaments, where gravity draws matter inward from multiple directions. Material flows along the filaments toward the nodes, feeding the clusters with a steady rain of gas and galaxies. A massive cluster might sit at the junction of several filaments, each one delivering fresh material from a different direction. The cluster grows as matter accumulates. Galaxies that form along the filaments fall inward along those filaments toward the cluster core. Dark matter accumulates. Hot gas fills the space between galaxies, heated to tens of millions of degrees by the energy of gravitational infall, glowing in X-rays so intensely that galaxy clusters are among the brightest X-ray sources in the sky. And at the very center of this structure, at the deepest point of the gravitational well, sits the dominant galaxy, the brightest cluster galaxy, the one that has been feeding longest and feeding most. Consider Able 2029, a massive galaxy cluster roughly 1.04 billion light years from Earth. This cluster contains thousands of galaxies bound together by a halo of dark matter so massive that the entire system weighs roughly 100 trillion times the mass of our Sun. At its center sits IC 1101, one of the most frequently cited candidates for the largest galaxy ever observed. IC 1101 is enormous by any standard. It is a supergiant elliptical, a CD-type galaxy with an extended diffuse envelope of faint stars surrounding a brighter core. Its stellar population is overwhelmingly old and red. There are no spiral arms, no star-forming regions, no blue young stars of any significance. It's a vast, softly glowing mass of ancient suns that have been burning for billions of years, accumulated through merger after merger, across the lifetime of the cluster. How large is it? This is where honesty requires care, because the answer depends on how you measure. Early studies of IC 1101, conducted in the 1990s and 2000s, suggested diameters as large as 5 to 6 million light years. If those numbers were taken at face value, the galaxy would be so vast that you could fit 50 or 60 Milky Ways end to end across its diameter. Those figures made IC 1101 famous. They turned it into a staple of popular science, a go-to example whenever anyone wanted to illustrate the sheer scale of the largest galaxies. And to be clear, the galaxy is genuinely immense. That is not in dispute. What is in dispute is the exact number you attach to its size. The problem is the halo. Giant elliptical galaxies do not have sharp edges. Their brightness fades gradually from a dense, luminous core outward into an increasingly faint envelope. That envelope keeps going. It gets dimmer and dimmer, the stars more and more sparse, until eventually the light from the galaxy becomes indistinguishable from the faint background glow of the sky itself, the scattered light of distant, unresolved galaxies, the thermal emission of the telescope's own optics, the irreducible noise of the detector. Where you draw the boundary between the galaxy and the background depends on how sensitive your instrument is, how carefully you subtract the background, and what surface brightness threshold you use as the cutoff. Choose a brighter cutoff and the galaxy appears smaller. Choose a fainter cutoff and the galaxy appears larger. There is no physically meaningful edge where the galaxy stops. The the stars simply thin out. This means that different studies, using different telescopes and different methods, can produce genuinely different size estimates for the same galaxy. More recent analyses of IC 1101, using modern data and more conservative definitions of where the galaxy ends, have suggested diameters closer to 2 million light-years. That is significantly smaller than the older estimates, but still staggeringly large. 2 million light-years is 20 times the diameter of the Milky Way. It is still among the largest galaxies ever measured. The revision does not diminish the galaxy. It simply shows that pinning down the size of an object with no clear boundary is inherently difficult, and IC 1101 is not the only contender. Other galaxies in other massive clusters rival or potentially exceed it, depending on which measurements you trust and how you define size. NGC 4889, the dominant galaxy in the Coma cluster, roughly 330 million light-years away, is another colossus. Its stellar mass is enormous, possibly exceeding that of IC 1101. Its central black hole, estimated at roughly 21 billion solar masses, is one of the most massive ever detected. NGC 4889 may be less spatially extended than IC 1101, or it may not be, depending on how deeply its faint outer halo is traced. Size and mass do not always track together in these objects. A galaxy can be extremely massive but relatively compact, or less massive but more spatially diffuse. Comparing them is not as simple as lining them up and checking which one is wider. NGC 6166, at the center of the Abell 2199 cluster, roughly 400 million light-years away, is another extraordinary example. This galaxy has multiple bright nuclei, the still visible cores of galaxies it consumed, but has not yet fully digested. You can see the ghosts of its meals sitting inside it. Distinct concentrations of stars that have not yet been fully dissolved into the host. Each nucleus is the remnant heart of a galaxy that once existed independently, now trapped inside the body of the giant, slowly spiraling inward through dynamical friction, eventually to merge completely. NGC 6166 is a galaxy caught in the middle of several simultaneous meals. Then there is Holm 15A, the central galaxy of the Abell 85 cluster, roughly 700 million light-years away. This galaxy drew attention because of its unusually large and faint core. The central region of Holm 15A is depleted of stars relative to what you would expect for a galaxy of its mass. Astronomers believe this depletion was caused by the merger of two supermassive black holes during a past galaxy merger. When two black holes spiral toward each other and merge, they gravitationally eject stars from the central region through a process called gravitational slingshot, flinging them outward and carving out a low-density core. The size of the core in Holm 15A suggests it swallowed a galaxy whose central black hole was itself enormous, and the resulting black hole merger excavated a vast cavity in the galaxy's center. The scars of cannibalism are not always on the outside. Sometimes they're carved into the very heart of the beast. And the list continues. The Phoenix Cluster, one of the most massive galaxy clusters known, roughly 5.7 billion light-years away, hosts a central galaxy that is not only enormous, but also unusually active. Unlike most brightest cluster galaxies, which have long since ceased forming stars, The Phoenix Cluster's central galaxy is producing new stars at an extraordinary rate, hundreds of solar masses per year. This appears to be happening because the hot intracluster gas at the center of this particular cluster is cooling rapidly, condensing, and falling onto the central galaxy, providing fresh fuel for star formation. It is a rare exception, a giant elliptical that is still actively growing, not just through mergers but also through gas accretion, building new stars from material raining down from the surrounding cluster medium. It shows that even the standard picture of red and dead ellipticals has exceptions, and that the feeding process can take more than one form. More recently, astronomers identified Alcyonius, a giant radio galaxy roughly 3 billion light-years away, whose total structure, including enormous jets of material launched by its central black hole, stretches roughly 16 million light-years from end to end. That measurement includes the radio lobes, not just the stellar body of the galaxy, so it is not directly comparable to the diameters quoted for IC 1101 or NGC 4889, but it illustrates the extraordinary scales that galaxy-scale objects can reach when you account for all the material they influence. The critical point is this: there is no single, definitive largest galaxy in the universe. The title depends on what you measure, how you measure it, and which component of the galaxy you include. Stellar halo extent, total stellar mass, dark matter halo mass, and total baryonic extent can all give different rankings for the same set of galaxies. The question of which galaxy is biggest is less like asking which mountain is tallest, where the answer is clear, and more like asking which cloud is largest, where the boundary of the object is fundamentally ambiguous. What we can say is that the largest galaxies span millions of light years, contain trillions of stars, and sit at the centers of the most massive galaxy clusters in the observable universe. Their exact ranking relative to each other is a matter of ongoing measurement and debate, not settled fact. But the most remarkable thing about these galaxies is not how large they already are. It is that they are still growing. This is not a figure of speech. It is an observable fact. Galactic cannibalism is not a process that happened long ago and then stopped. It is happening right now. It has been happening continuously since the first galaxies formed, and it will continue happening for billions of years into the future. We see it in our own galaxy. The Sagittarius dwarf is being consumed as we speak. The Magellanic Clouds are being slowly stripped. In 4.5 billion years, the Milky Way itself will merge with Andromeda. Our galaxy, the one we thought of as everything at the start of this journey, will be consumed. It will lose its spiral arms. Its disk will be disrupted. Its stars will be scattered into the chaotic orbits of a new, larger elliptical galaxy. The Milky Way as we know it will cease to exist. We see it in the clusters. Galaxies falling inward along filaments are arriving at cluster cores today. Deep imaging reveals tidal streams and shells around brightest cluster galaxies that are fresh, cosmically speaking, produced by mergers within the last billion years. The growth is not a relic. It is ongoing. We see it at higher redshifts, looking back in time. When astronomers observe galaxy clusters as they existed billions of years ago, they see the central galaxies smaller than their present-day counterparts. They see more mergers in progress. They see the assembly happening in real time across cosmic history. The further back you look, the smaller the central galaxies are, and the more actively they are feeding. The growth rate was faster in the past, when the universe was denser and mergers were more frequent, but it has never stopped entirely, and there is no natural mechanism to make it stop in the future. As long as galaxy clusters exist, as long as gravity continues to draw smaller galaxies toward the center, as long as filaments continue to deliver fresh material from the cosmic web, the brightest cluster galaxies will continue to grow. They will consume every satellite that falls within their reach. They will absorb every tidal stream. They will add layer after layer to their halos. There is no off switch. There is no maximum size imposed by the laws of physics. There is only the supply of material and the time available. Given enough of both, the central galaxy simply keeps getting bigger. In the far future, billions or tens of billions of years from now, the expansion of the universe will change this picture. Dark energy is accelerating the expansion of space. As the universe expands faster and faster, the filaments of the cosmic web will stretch and thin. The flow of new material into clusters will slow and eventually stop. Galaxies that are not already gravitationally bound to a cluster will be carried away by the expansion, beyond reach, beyond contact, forever. The clusters will become isolated islands, cut off from the cosmic web, no longer fed by the filaments. But within each island, gravity will continue its work. The galaxies already inside the cluster will continue to sink towards the center. The central galaxy will continue to consume them, one by one, over timescales of tens or hundreds of billions of years. Eventually, in the very distant future, each cluster may be reduced to a single colossal galaxy, the merged remnant of every galaxy that was ever part of that cluster, surrounded by an expanding void of empty space. Every star, every remnant, every trace of every galaxy that once existed independently will have been absorbed into one final structure, the ultimate product of hierarchical merging, floating alone in a universe grown dark and cold and empty. That is the trajectory. That is where the process leads, if you follow it to its logical conclusion. Not to a universe of many galaxies, but to a universe of a few isolated supergalaxies, each one the graveyard of thousands of predecessors, each one carrying within itself the fossilized remains of every galaxy it ever consumed, drifting through an expanding emptiness with no new material to consume and no neighbors left to devour. Step back now and consider the full arc of what we have seen tonight. We began with our own galaxy, the Milky Way, and it felt like everything. 100,000 light years of stars, hundreds of billions of suns, a structure so vast that light itself needs 100 millennia to cross it. From the inside, standing on a small planet orbiting one ordinary star among those hundreds of billions, the Milky Way seemed limitless. Then we learned it was not. Andromeda is bigger, the oversized spirals are bigger still, and the giant ellipticals that sit at the centers of massive galaxy clusters are bigger by an order of magnitude, stretching millions of light years across, containing trillions of stars, so enormous that our entire galaxy could be dropped into their halos and disappear without a trace. And then we learned how they got that way. Not through superior star formation, not through some exotic physics, not through any mechanism that created something from nothing. They grew by eating. Every star in their halos was born somewhere else. Every chemical signature in their stellar populations tells the story of a galaxy that once existed independently, and now exists only as a layer of light in the body of the giant. They are not creators. They are consumers. The universe builds its largest objects not by construction, but by consumption. That is a profound and unsettling truth. The most magnificent structures in the known universe, the largest individual things bound together by gravity, achieved their magnificence not by building something new, but by destroying everything around them and keeping the pieces. Their beauty, if you want to call it that, is a beauty assembled from wreckage. Their size is the accumulated mass of hundreds of devoured galaxies. Their faint, ancient, golden glow is the combined light of trillions of stolen suns, and they are still at it. Right now, in clusters scattered across the observable universe, the central galaxies are feeding. Smaller galaxies are spiraling inward, being stripped, being stretched into streams, being dissolved. Shells are forming in the halos of giants as the oscillating remnants of recently consumed companions pile up at their turnaround points. New layers are being added to the fossil record. The biggest galaxies are getting bigger, and they will continue getting bigger for as long as the universe provides them with something to eat. Our own galaxy will join this process. In 4.5 billion years, the Milky Way will begin its merger with Andromeda. The spiral arms will be torn apart. The disk will buckle and dissolve. The stars, including our sun, if it still exists by then, will be scattered onto random orbits in a new, larger elliptical galaxy. Everything familiar about the Milky Way, its shape, its structure, the night sky as seen from Earth, all of it will be erased. Our galaxy will be consumed, just as it has consumed others. There is a strange symmetry in this. The universe began with simplicity, hydrogen and helium, forged in the first few minutes after the Big Bang, spread across all of space. Gravity pulled that gas together into the first small galaxies. Those small galaxies merged into larger ones. Larger ones merged into larger ones still. Each generation consumed the last. Each step up the ladder was paid for by the destruction of what came before. The galaxies we see tonight are not the originals. They are the survivors, the winners of a billions of years long competition, in which the only rule is that the biggest gravitational well gets the most food. And the very largest of them, the supergiant ellipticals at the centers of the most massive clusters, are the ultimate expression of that rule. They did not merely survive, they dominated. They sat at the deepest point in the deepest well and consumed everything that fell within reach. They are still consuming. They will continue consuming. They are the universe's answer to a simple question. What happens when gravity has billions of years to work and nothing to stop it? The answer is written across the sky in the ancient golden light of the largest galaxies ever found. They keep growing. There is no reason to stop. And the universe, patient and indifferent and vast beyond all human comprehension, simply lets them.